Yeah, so some of the things that my students and I have been working on, the goal of our lab is really looking at sensor data and applying machine learning techniques both on devices from the data produced by sensing devices by mobile phones. And this is just a snippet of that in the context of healthcare-driven applications. So smart healthcare is a big area of research these days. We're seeing a lot of activity around electronic health records, specifically in the context of what I'll be discussing. Also around smart devices that people are placing on their bodies in order to enhance performance, in order to do prediction of health related issues. And one of the areas that is really interesting now is also looking at not just sensors that you place on the body, but also combining them with things that you may place in the environment itself. So today I'm really going to be focusing on two aspects of that, and going forward how I may bring those two together. Specifically, the motivation for the first part of the talk is that the number of people in the United States that are 65 and over will nearly double by 2030, which is very soon. And almost 90% of them want to stay at home as they grow older. And that means that we have to build the right infrastructure, in order to maximize quality of life as folks get older. So there's a question of what kind of infrastructure can we build? How useful will it be as part of a larger ecosystem for evaluating and tracking health at home? We're seeing, as I mentioned, lots of activity around various silos of this. I think the vision is going forward that these will eventually come together and that the various stakeholders will play a participatory role both in producing and analyzing that data and closing the loop with doctors and medication. And so in the broader context of this general area, I'm going to discuss specifically how we're looking at the mobile phone, which has reached high levels of penetration in order to extract useful information from the sensors produced on mobile phones. So naturally, lots of people have mobile phones. Ages ranging from very young to very old. And we want to leverage the fact that these phones are essentially computers with sensors that are on them in order to understand how people are living out their daily lives at home. One area that is very important is, for instance, taking your mobile phone as you're walking around and being able to classify what it is you're doing throughout the day. Essentially classifying those into these fixed sets of classes of how often you're standing, sitting, laying down, etc. throughout the day. And what's interesting is that if you look at the distribution of these activities over time, you can start to correlate that with the development of diseases, the progression of diseases, the improvement of health, or the deterioration of health overall. So this is a sort of foundational piece in a larger pipeline for being able to do that. Human activity recognition is an area of active research, and it's being looked at from various angles. From the vision angle, it's been looked at for a long time, where you're doing pose estimation and then classifying various poses into various types of activities, like the ones I showed in the previous slide. We've seen lots of products out in the market. Here's an example of the Philips Direct Life sensor that you wear as a necklace. And it has an IMU sensor in it, and as you walk around, it essentially classifies it into various activities you're doing throughout the day. This is mostly so that you can evaluate how active you've been throughout the day, but going forward, I think with an older population, you also will use the distribution in the various types of activities to evaluate how well people are progressing. So one area of human activity recognition with inertial measurement units on a phone, here's a data set that has been studied quite extensively. They take the inertial measurement unit data, which is a gyroscope and accelerometer, which sits on your phone, and derive 561 features. It's actually quite rich a data set that's used for evaluating classifiers that are built on top of the data. The features that are extracted are these statistical summaries over windows of readings, and then those are various classifiers are essentially built in order to evaluate the performance. Our general observation with this data set and several others is actually that the features clearly are not independent since they're all derived from the raw readings. And so one of the aspects that we were looking at is, well, these actually live on a low-dimensional manifold, and in fact, you don't get much more performance, maybe any performance gain really, by having 561 features extracted from 12 different sensors. There was also, a few concerns that we had. One is if we want to get this on a mobile phone, one of the things we can do is you can design to keep the mobile phone dumb, which is essentially the mobile phone collects data and sends it to the cloud and all the complexity is there. There are issues with latency if you want to do anything in real time and maybe build applications on top of that. There's also issues with privacy. So the challenge that we went ahead and tried to solve is how much can we leverage the mobile phone itself for collecting this data and doing local classification. So our approach is, never mind the fact that there's 561 features. As I mentioned, most of them are not independent anyway. Let's use the 6 channels we're getting from the raw IMU signals. We borrowed a technique called recurrence plots, which actually create these visual images of multivariate time series data. And the reason we did this is because image processing pipelines are very, very robust and very good. You can train them and they perform quite well. And there's many of them available. So there's many flavors that you can try out of the box. So one challenge is, great, we know that if we can cast this problem as a visual classification problem, chances are there's going to be lots of classifiers that do very well on them. The other problem we have going forward is, can we actually take some of these things that we're grabbing out of the box, available in open source, and actually run them on the phone itself? And just as an example of some of the images that are generated from these recurrence plots, you can take these multivariate time series signals, the details of which are in the literature, and generate plots that look like this, which are clearly visually distinguishable. And so, most of the classifiers actually have no trouble telling the various activities apart using recurrence plots. So our next challenge is, great, well, we've now cast this multivariate time series problem into the image classification domain. Lots of work there. Let's take one of them. Let's take the best one, ImageNet, this huge, deep neural network, and see how much of it we can strip to get onto the mobile phone without compromising accuracy. There's also some work called MobileNet, which is essentially trying to do the same thing of stripping the deep network for the Inception network. Sorry, not ImageNet, the Inception network, which was trained on ImageNet. And it's essentially a small version of Inception. So we ourselves took the deep network and stripped it apart to get all the essential components given these recurrence plots to get high performance, and then compared it with MobileNet, which was precisely designed to run on mobile phones, to see how close we can get to this sort of mobile phone optimized network. And so starting with these 6 IMU signals down from 561, we can generate the image using the recurrent plot generation algorithm, feed it into a deep CNN network, this ImageNet network or the MobileNet network. Certain things that we realized as we were going through and feeding it to the network is actually most of those layers, remember, these are general purpose image classification networks. Here, we're not seeing quite the same amount of diversity in the underlying distribution that you're training these networks on. So lots of the network is redundant. And so we started stripping out layers. 95% of the network, in fact, came from the fully connected layer at the end. And we can strip out all but 2 of those, I think, 27 layers that were in the network. So while we started with these very deep networks, general purpose image classifiers for this particular domain of problem, most of those layers are not necessary. We can throw those out. That reduces computational overhead and reduces the space taken up on the phone. As I mentioned, since we only have somewhere between 6 and 12 different types of classes, depending on the data set that you decide to train on, in fact, the task is a lot easier. You can replace this classifier with a shallow network, a shallow model in the SVM, and get very similar performance. And now the entire thing fits on the phone. You can run it in real time, and you can build applications off of it. And so just to go through some of the performance, we played around with evaluating Inception and MobileNet, retraining it from scratch using these plots. Here we see that actually MobileNet always outperforms our stripped Inception model, getting anywhere between the high 70s all the way up to the mid 90s in terms of classification accuracy. Now, if we use the weights that were actually learned in those first few layers of these networks, we do a lot better. So we've tried first taking the network architecture and training it from scratch. Naturally, these are not trained on anywhere near as much data as what Inception is trained on. So those weights we expected to do better. We almost got perfect performance in terms of classification accuracy on 2 very different data sets using different sets of classes and everything else. And the best part is you just inherit the weights of those first few layers. It fits entirely on the phone, and it runs in real time. Okay, so existence, yes, there is a solution, and we can build on top of it. So that was good. So now we're looking at virtual sensors as well. In the context of virtual sensors, what we mean is, no, I don't want to wear it. It does reduce quality of life, especially for the very elderly. So what can we do about that? And we already saw a presentation that talked about using wireless signals for doing that. Here, we're examining the use of video. So video has been used extensively. We see that for the elderly folks or very elderly, exercise is extremely important. Evaluating how often people are exercising who have various diseases, such as congestive heart failure, is very important. Even as you reach older age, of course, it's very good for you to be more active rather than less. And just getting a sense of that so that your doctor can put it into a broader scope of how your health is progressing is very useful. So, the idea, of course, is, can we use video? Video has been used a lot and in many applications. To what extent can we, again, take something that we can grab out of the box, and how well will it work for supporting applications where we want to extract meaningful information about daily activity of a patient. Mostly on the market, it seems there's no requirement for comfort. It just, the data has to be good. And you can see that, especially for the very elderly, this is a major problem. They remove sensors. It reduces quality of life quite significantly. And so that was one of the main motivations for examining the generation of virtual sensor data from ambient sensors in the environment, in this case video. Since we already have a rich pipeline for evaluating time series, well, why not cast it as a time series problem in the same way we casted the other one as an image problem? And of course, the image community is quite mature in this respect. We can see that they can do multi-human key point extraction. And so we said, hey, can we start with these networks and maybe strip those out to make them smaller, specialized for this application? Can we use these networks to generate streaming virtual sensor data for us? And then can we use that to generate IMU data and feed it into pipelines for doing human activity classification? For a single person, not very difficult. It's sort of the standard base case. Here, what you're seeing on the left of the screen is the sensor data being extracted from that network that was doing the multi-person version of the problem. You essentially get these two-dimensional coordinates of each of the key points on the body, which includes several key points along the shoulder, the head, the legs, and your arms. For multi-person, we had to hack it a little bit in order to be able to pick out how many people were being detected in the image, and then strip out each of the key points per person and generate the two-dimensional stream of pixel coordinates for key points. And of course, that only tells you what part of the problem is. That doesn't get you all the way there, but at least now we have these sort of virtual sensor stream in a different coordinate space for evaluating multivariate time series. Image geometry is quite involved, well understood, however, and so naturally you'd like to go from one image plane to another. You'd like to go from the pixel plane to real world coordinates and back. And this is essentially a well understood problem. You can do forward projection from the world coordinates down to pixels. We were grabbing the pixel coordinates. Is there a way of going back? Well, for many of these networks, they require lots and lots of samples, lots and lots of ground truth. Over time, what we ended up finding is this nice model that has this another very deep network, but that rather than use ground truth actually does 2D projection from pixel space to world world coordinate space, and back down to 2D projections, minimizing the reprojection to 2D in comparison to the 2D that was fit in. And that's because 3D coordinate labeled data sets are sparse. They're sparsely labeled. And so now, actually, we're currently in the process of taking the stripped out version of the model and applying the same concept here, maybe doing some retraining. And the idea now is once we actually have those multivariate coordinates, then we can look at, we can do all the things we typically do with time series, right? We can start to either generate these images to do activity classification. We can find clusters of similar time series shapes. Once we can generate this multivariate time series in 3D space, we can cluster them, look at the evolution of clusters. So for instance, if you are an athlete, you'd like those clusters to be nice and tight for the position or the sequence of moves that you happen to do. Say you're a pitcher, you want your arm slot to be consistent. If you are recovering from injury, you actually want those clusters for the same activities to actually be a little bit broader. And so our hypothesis now, which we're in the process of testing, is how well we can capture that in the cluster shapes, right? So once we have these multivariate time series signals and we can separate them into different positions and transitions between them, now we can look at cluster shapes over time as patients get better or get worse and see if how closely those are correlated with both the progression of a disease or the improvement of movement and various others. Okay, and so of course, you can identify risks. You can, in the case of sports, you can compare players. In the case of yourself, you can compare yourself before and after an intervention, and that's sort of ongoing work right now in the lab. So there's some other work that we do in other areas as well, but I'm happy to answer questions about what I just presented.